Okay, welcome to section 4.3. We're going to look at definite integrals. Our objective today is to evaluate a definite integral using the properties of definite integrals. What I want you to understand, what is very important that you understand, is that the area under the curve can be represented by an integral. So in other words, if I wanted to find the area under the curve f of x, I would integrate the function from a to b, and that will give me the area under the curve. Now what makes the integral definite is I'm integrating from a to b. That means that it is bounded and it's a definite integral. So if I were to do this example, I want to start by graphing it. Now we could do it analytically. I'm going to do it both ways, but I want to start by simply graphing it. So if I were to graph y equals 2, that is a horizontal line at y equals 2. So I want to know what is the area under the curve from 0 to 2. So that would look sort of like, I want to know what is the area, I'm sorry, from 0 to 6. I want to know the area from here to here. This area is what I'm looking at, okay? So anyone can tell me, hopefully most of you can tell me, that the area under the curve is simply, for a rectangle, is length times width. I'm sorry, I already have that typed. And we can see that the height of this rectangle is 2, and the width of this rectangle is 6. So the area for this rectangle is 6 times 2, which is 12. Now, if I were to do this analytically, what I want you to see is that because it's a definite integral, because it has 0 and 6, I no longer need plus c. And what I'm saying is the integral of 2 is 2x, we know that, and then I'm going to evaluate that from 0 to 6, and that notation looks a little bit like this. So the first thing I do is I put 6 into this equation to get 2 times 6, and then I put 0 into there and get 2 times 0, and I get 12 either way. Once again, we're going to graph this first. And when I graph this, I get a linear function, and I'm evaluating it from -1. So we have to imagine there's a line here and 4. So there's a line here. Now, what shape does this make? So I'm looking for the area under this curve. What shape does this make? Well, recall from geometry, this is a trapezoid, where this is base 1 and this is base 2. And the height of this trapezoid, which is perpendicular to the bases, would be from -1 to 4. The height would be 5. So B1, I think, is 2, and B2 is 7. So we're going to use the formula for a trapezoid to find the area under this curve. And we get 45 over 2. Now, can we do this analytically? Absolutely. Remember, we're going to integrate. And we're integrating from -1 to 4. X plus 3 gives us x squared over 2 plus 3x. Now, I put c here, but it's not needed. And I think I put c to show you that it would just zero out. And so I'm evaluating this from -1 to 4, meaning that I'm going to put 4 in for x, and then evaluate that, and then 3 in for x. Now, what I did here was I showed you why we don't need c, because I'm going to add c here, and then I'm subtracting c here. And the c's just kind of zero each other out. So they're not necessary. We get the same answer. Now, for this particular problem, at this point in our math career, we cannot integrate that. So we can only evaluate this graphically. So what I need you to understand and know and recognize is that this is the formula for a semicircle with a radius of 4 centered at 0. I'm sorry, radius of 2 centered at 0. So now I can find the area of this under the curve just by knowing the formula for area. So I get approximately 2 pi. or I get 2 pi and approximately 6.283. Remember, always take it 3 places behind the decimal. So there will be some functions where you cannot integrate analytically, and you'll have to be able to use the area under the curve to solve it. Now, for the next 3 problems, all I'm asking you to do is set it up. So this is just very simple. I'm just asking you to set this up. So what I'm looking for is the area under this curve from 0 to 2. And that's just how I'm going to note it. The only thing you need to make sure you know is that your limits, and you need dx. You need to tell me I'm integrating with respect to what? The next one, the function this time is x squared, and we're integrating from 0 to 2. The function is 1 over x squared plus 1, and we're integrating from -1 to 1. That's all I need you to do for that. That's pretty simple. Okay, let's talk about net area under the curve. Net area under the curve means that we consider area under the x-axis as negative. So anything under the x-axis, we consider that negative area. Now, I know in the past you've been told that there's no such thing as negative area, but in calculus, we like to break all the rules. Here's some properties of integrals that you really want to know, and you're going to see this on the AP exam. So notice the difference between those two is that I flipped the limits. So if I flip the limits, then it becomes reversing the limits, change the sign. If I integrate from a to a, then the net area under that curve is 0. Think about it. So I'm integrating from a point to the same point. So there's no area under the curve, so that would be 0. If I have a function and it's being multiplied by k, and I think we talked about this yesterday on the last video, you can just pull out the k. This is a trick that you really don't need to know. I'm just saying that there's no x in the original. It's just a constant dx. Well, that's just going to be b minus a times c, where c is any constant. You can break up two integrals. So if I'm integrating from a to b, so the sum of the integral is the integral of the sum. So if I'm integrating f of x plus g of x from a to b, I can then make that two separate integrals and integrate f of x from a to b and g of x from a to b. So they could be added or subtracted. If c is some point between a and b, so for instance, if I'm integrating from 1 to 5, then I can integrate that from 1 to 3 and then 3 to 5 and get the same answer. So as long as in this particular problem c is between a and b, I can break that up with any value of c in between the two, between a and b. So the intervals themselves can be added or subtracted. We really want to know properties of even and odd functions. So remember, an even function is symmetrical about the x-axis. And the AP exam loves to use symmetry. So if I have a function, and let me see if I can draw a function that's symmetrical about, just imagine that this is symmetrical and this is negative a and this is a. I can integrate, and sometimes it's easier, especially if I'm integrating by hand, I can integrate from 0 to a, and because it's even, then I just multiply by 2. So essentially, I find the area of this side and then double it. If a function is odd and I integrate from negative a to a, I get 0. And the reason is, let's think about, y equals negative x is an odd function. And I'm integrating from negative a to a. Well, what happens here? This area is positive, and this area is negative, and it's the exact same area. So this positive area plus this negative area makes it 0 out. Let's do some examples. My suggestion to you is once again that you pause the video and then come back and see the answers. Okay, so the first one is 0 because we're integrating from A to A. For this one, we're going to pull out the 15, and we notice up here that the integral from 2 to 4 of dx is 2. So then this just becomes 2, or 15 times 2. For this one, we can break this up into two integrals. We know the integral from 2 to 4 of x cubed, and then we know the integral from 2 to 4 of 4 dx using this one. So we can break that up into two integrals. For the next one, once again, we can break that up into 3 integrals. And using the information that we have, we can find the sum.